Okay, welcome to this video on internal resistance. Right, here is a circuit diagram showing a cell and a resistor in series to each other. And here's a picture of a cell, okay, carbon zinc cell, and here is an equation to do with internal resistance. Okay, so let's start. The first thing to notice here is we've got this Greek E symbol here. This represents what's called the electromotive force. Electromotive force is the voltage that is produced by the reaction of the chemicals within the cell. Now, any two sets of chemicals that react with an oxidation reduction reaction with each other have a potential theoretical voltage that they could give out. Now, due to problems that arise, this isn't always the voltage that we get out of a cell, but we'll look at that later. Okay, so that's the EMF, the potential voltage that is produced by the reaction of the chemicals. We also get, because of that, what's called a supply voltage. Now, the supply voltage is actually the voltage that is measured from the terminals, that is the positive and the negative terminals on the outside of our cell. And notice that our supply voltage here on the circuit diagram is measured by the voltmeter touching on the outside of this dotted rectangular box that represents the cell, and it would be, if we were to measure it on this cell here, it would be from the positive terminal at the top and the negative terminal at the bottom. We would measure the voltage from the outside. That's called the supply voltage. So now we've got two concepts so far. We have the theoretical voltage, the EMF, and the supply voltage, that is the actual voltage that we measure from the outside of the cell. Notice here, if this was, we were using Kirchhoff's law here, the loop law, that we could say that the supply voltage here would equal the voltage that was used by this external resistor. Okay, so I guess the concept here that we're really trying to look at is called the internal resistance. Now, the internal resistance is this phenomena that comes about because the chemicals reacting inside the cell actually have to physically get somewhere before they can react. And in order to get somewhere, if we think about the manganese oxide within this paste, they will actually have to jostle past other particles or chemicals, and in that process they will give out heat, they will lose some energy, or they're going to lose some voltage, and this is going to have that will produce some resistance, which is why this is called internal resistance. Internal resistance because it's resistance that happens within the cell. It's resistance that happens before the voltage is released from the cell. So in reality, this internal resistance will cause the cell to use up some of its theoretical voltage before it is given out. So we can work out how much theoretical voltage is used up by multiplying the current by the internal resistance. And we can work out the supply voltage by taking this voltage used up from our calculation of internal resistance away from our EMF. Okay, just reiterating again, this rectangular box here, dotted box with the cell symbol inside and the resistance symbol, is actually our cell. Okay, and this here is actual a diagram of an actual carbon zinc cell. What you might find is an AA battery, or a C or a D battery, we call it, which is actually a cell. Okay, so here's a closer up look at this cell, and we can see some important aspects of it here. This bit along the middle is the central electrode. Notice it doesn't actually touch the bottom, and it's connected to the positive electrode on the top. We have this outside casing here, which is actually underneath whatever the label is on the outside of the battery, is made of zinc, and it physically touches this bottom electrode here. You can't see this at the top, but the actual outside zinc coating doesn't touch the positive electrode at the top. So we've got two different electrodes, a positive one and a negative one. Now, at the metal case on the outside actually is made of zinc metal, and it undergoes a reaction where it turns into zinc ions, zinc 2+. In that process, from going from zinc metal to becoming a positive zinc ion, it has to lose electrons. Those electrons are the easiest path for those electrons, the only path those electrons can take, is to flow around the circuit here. So they're going to flow in this direction towards the positive electrode. Now, in order to do that, they have to travel through the resistor here. And any energy that these electrons have that was produced by this cell will be used up by this resistor. So they're all going to travel along until they get to the positive, this internal positive electrode here, and then the electrode in the middle here is going to donate the electrons that have arrived, and it's going to give them to the molecules within the paste, in this case the manganese oxide molecules. Now, these molecules, because they have to actually touch the electrode here, molecules that are further away from the electrode have to move all the way to the electrode, and in doing that they have to move past other molecules. They'll bump into them, they will lose some energy to friction, to heat as they move through there. So that is some of the potential voltage that they could have had to complete their accepting electron reaction that is lost to heat, and that is why we lose some of the voltage, and we call this loss of the energy of heat internal resistance. Now, here we go, here's the cell again. This is the actual chemical reaction. We've got manganese oxide reacting with zinc, and it's producing these the zinc ions and this manganese, 2 oxygens and a hydrogen. And now the EMF, the theoretical voltage here, is 1.62 volts. Of course, that isn't going to be the voltage that comes across from the terminals, because we just talked, I just talked about that these manganese oxide molecules will lose some of the voltage, some of the energy as they travel towards the electrode. If I only have a very small current coming off here, then only a small amount of these molecules need to actually collect electrons. It will be the ones that are really close to the electrode, because they're the easiest ones to collect the electrons, and they're very little internal resistance because they don't have to move past many of the molecules. However, if I take a large current off this cell, then we're going to have lots of manganese oxide molecules get to this electrode very quickly. Now, the molecules that are adjacent to the electrode will not be enough to collect enough electrons to produce the current we want. Therefore, we're going to have to take ones from further away. Because we're taking more from further away, and because they're all moving at the same time, we produce a lot more friction, a lot more heat, and we lose a lot more voltage. So actually, when we draw a large current from a cell, our voltage at the terminal will decrease because there will be a larger internal resistance. So how does internal resistance of a fresh battery compare to that of a flat one? Well, if we think about that, if a fresh battery has lots of manganese oxide, I mean, it's chock-a-block full of it, and that means there will be lots of fresh manganese oxide right next to this electrode. And if they want to collect an electron, they have to do very little movement at all, so there's going to be very little internal resistance. However, the definition of one that is flat is that most of these chemicals, the manganese oxide or the zinc, have been used up, and there's a small concentration of manganese oxide. If I tried to draw a current off a flat one, what would happen is that there would be very few manganese oxide molecules adjacent or near the electrode in the middle. And in order to get enough to supply the current, they would have to come from throughout the paste, further away, in the medium distance, close, and so all of that would produce a lot of internal resistance as they move there. So we would expect a flat battery would give us a low voltage. Okay, let's move on to the next point. Next point is, okay, what types of calculations are they going to ask us to do? The type of calculation they're going to ask us to do involving internal resistance is one where we use this equation, okay, the supply voltage equals the EMF minus the current times the internal resistance to solve an unknown. So usually what will happen is we will know three of any one of these variables, and we'll have to solve for the other one. So in this case, they've told us two. Okay, so they've told us what the EMF is, 12 volts. They've told us what the current is, 3.2 amps. Right, they've also given us a diagram, which is a hint that we've got another step to do before we actually use this equation down the bottom. Now, what we can actually do with this diagram is use one of Kirchhoff's laws, the Kirchhoff's loop law for voltage. That is, the voltage that is being used by this resistor here is going to equal the voltage of the power supply, or the supply voltage across this cell. So how do I work out the voltage here that is used? I use Ohm's law. Okay, so I use voltage equals current times resistance. I chuck in the current and the resistance, and I get the voltage is equal to 10.54 volts. That's how many volts is used across this resistor. If that many volts is used across the resistor, then that many volts must have been produced from the supply voltage. Okay, so now I know the supply voltage, I know the EMF because they've given us that, I know I, so I know three variables, I chuck them into my equation and I solve for R. And then I get, okay, the internal resistance in this case is 0.45 volts. Now, of course, we could they could have, for a start, given us what the internal resistance was and left us to calculate the EMF, but it's all very similar. In any case, for any one of these problems that we need to solve, we're only going to need to use Ohm's law and rearrange and solve for one of the variables. Okay, I hope this has helped. Thank you for listening.